Welcome to our webinar, Design, Deploy, and Manage Edge Computer Vision. I've been working on LEIP Design for the better parts of 3 years, and as a team lead, designer, and developer, I couldn't be more excited to share this product with you. My goal with this webinar is to introduce you to LEIP Design and give you a good understanding on how you can use it in your organization. Maybe you'll find that it fulfills a need that you currently have. Or maybe you'll see opportunities that you didn't know were available. Imagine this. You can start training a computer vision model in minutes instead of months without any prior machine learning expertise. Not just that, but I'm about to show you how you can predict the deployed performance of the model even before you begin training and use your project requirements to drive your machine learning choices. I'll start by discussing the common pain points faced in Edge AI deployment. Then, I'll introduce LEIP Design and how it allows you to quickly and confidently train models based on your set performance and hardware requirements. Finally, I'll open the floor for questions. Our goal today is not just to present our solutions, but to engage in a dialogue that helps you understand how LEIP can help your Edge AI initiatives. Let's get started. Until now, Edge AI has been complex, slow, and far more likely to fail than succeed. This is an important reality because it's a challenge that you all face. 85% of machine learning projects will never make it to deployment. Why is that? In our careers, we've seen how guiding any complex project through success requires tremendous amount of communication and collaboration across diverse teams. It's no different in machine learning, where you have your data scientists, your ML engineers, integration and deployment specialists, all having to coordinate. In machine learning, the problem of communication is exacerbated by the lack of available data. The field is just so new that not a lot of information is available to support decisions. What we've seen time and time again is that attempts to train and deploy machine learning models are constantly fraught with a lot of error and are almost always plagued with inefficiency. A typical example is your machine learning engineers train a model that makes them happy. They have a highly accurate model, and that's great. But then your deployment team spends the time and resources to finally put the model in the product, and it turns out to be too slow or too big, where the model is eating up all the available memory on that particular embedded hardware. This issue of only finding out after you deployed that the model is not appropriate happens more often than you think. At this point, should you change the inference hardware to a more powerful alternative? Maybe give up on the whole idea of edge deployment and go into the cloud. Or go back to your machine learning engineers and ask them to restart the model exploration and restart the training process with a smaller model. We're talking months of effort wasted. Perhaps if only your machine learning engineers had opted for a more appropriate architecture, this issue could have been avoided altogether. But there was no way for them to have known how the model would perform after training, optimizing, compiling, and packaging it for that target hardware. I'll give you another example. Let's say requirements about the speed on hardware were specified at the start of the process. But in the months that it took for your data engineers to get the data ready and the machine learning engineers to select and train the model that would meet those requirements, better hardware became cheaper. Do you go back to the lab and have them restart the design with this new information in mind? Or do you just eat the hardware cost so as not to delay your project any further? What we've seen time and time again is that there are two main issues that plagued machine learning product development and are responsible for most failures. The first one is lack of data on how choices made today affect the downstream performance. The second is difficulty to make changes to those choices when the need arises. These two are the biggest barriers that lead to slowing down product development and, in most cases, failure. At Latent AI, we have now been able to overcome these barriers for quick machine learning product development. Our tools lead to better decision-making, fewer surprises in the development process, and the ability to course correct as changes arise. How did we get here? We created the concept of recipes. Recipes define everything about the end-to-end modeling and deployment process, from how the data is ingested and augmented to how the model is trained and optimized for a specific target hardware. In our headquarters, we have a device farm with a range of all types of hardware devices, from GPUs to Jetson to embedded chips. With this concept of a recipe in place, we're automatically and continuously searching, really mining for the best recipes for each individual target hardware and application. This automated process results in a recipes database that currently has over 50,000 machine learning component combinations and configurations. And this database continues to grow. You can use our recipes database to filter the super large space of all options you have for your machine learning process. A space that includes model architecture, training hyperparameters, data augmentations, compiler optimizations, and much more, and keep only the paths that are viable based on your project requirements, like inference speed, memory, or energy consumption. This groundbreaking approach allows users to select with confidence the right training setup, eliminating all downstream surprises. Let's walk through some real use case scenarios. I'll give you an overview of each scenario and how it looks without our tools, and then how much it changes when we leverage the power of LEIP Design. Scenario number 1. Imagine needing to deploy a model to a particular device with strict inference speed and energy consumption requirements. Choosing the right model family, architecture, and tuning parameters can be daunting. Why? First, there's little to no information out there on the deployed performance of models. You really don't know how fast, how big your model will be once deployed on that target hardware. Second, each model family comes from a different source with code that tends to look and feel totally different. Training hyperparameters will need to be tuned for each architecture, meaning what works well for one family may not work well for another. Even the very basic step of loading your data so that you can train may require many engineering hours and reformatting. These are some of the reasons why making a model family decision is not just hard, but it's also hard to change later on. Now let's talk about how you would do this with LEIP Design. So again, scenario 1 is all about finding the right detection model to train that would meet your requirements on the hardware. We talked about having some requirements for inference speed and energy consumption. This could come from constraints in the field, like time that you have between charging a battery or the speed that you need to fly your drone through. So this would impose some inference time, inference energy, inference memory requirements on your recipe. Now, let's give some hypothetical values to those. So we need to deploy on a Jetson AGX Orin. That's the device that we have access to. We need our model, once deployed on the Orin, to run faster than 10 milliseconds per inference, and our model can't consume more than 200 millijoules at every inference. Let's go here and look at our LEIP Recipe Explorer. We talked about LEIP recipes coming in a database. This database is called a Pandas data frame. It's kind of like the Excel sheet for data scientists. So what we have here is just a visualizer over that data frame that we can filter, sort, and look in a bunch of different ways, depending on what's important to us. So on this left bar, I'm going to select the target architecture to be the AGX Orin, so that I only see recipes that have been successfully deployed and benchmarked and perform well on the AGX Orin. So that already filters out some of my recipes and changes our graph a little bit. You can see here on the y-axis, we have accuracy relative to best. Of course, you may be asking, how come you have accuracy if you don't have my data set? This is accuracy based on the data that we have trained, and we are constantly growing our volumes of recipes so that as time goes on, you can find a volume that is statistically very similar to your data, and the recipe is, let's say, statistically likely to translate to a very good recipe for your data as well. On the x-axis, we have inference speed, which is measured in frames per second. Now, if I look back to my requirements, I had the inference speed measured in milliseconds per inference. I'm going to go here on the x-axis and change the metric that I'm going to see on the x-axis to inference time on device in milliseconds. That changes my graph. That's great. Now let's look at faster than 10 milliseconds per inference. We can see here there's a lot of recipes that fit my inference time envelope. We've already kind of done the research and we've done the benchmark so that you don't end up training any recipe, for example, YOLO V5 extra large or so on, that would not meet your requirements envelope. Now let's look at our third requirement. We can't consume more than 200 millijoules per inference. So I'm going to open the larger menu for each of these recipes and just take a look at the energy per inference and see if we have anything that's below 200 millijoules. So on this particular recipe that I'm hovering over, the second row says energy per inference on device in millijoules. It's 52 millijoules. This one says 102, 92, 125, 163, 125. Okay, so it looks like we have definitely many recipes that would meet our three requirements of deploying on the AGX Orin, faster than 10 milliseconds per inference, and less than 200 millijoules per inference. Great, now we've answered this question essentially, that our requirements are realistic, that we can meet them. And we've already kind of seen that there's a space of recipes that would fit. I'm going to go and explore now this data frame. You can see that for each recipe ID, we've benchmarked with multiple devices, we have quantized with multiple different techniques, and we have the results of each of these experiments. I'm going to go and filter our large data frame of all results, again, just like we did on the visualizer, for only the stuff that has been benchmarked for the Orin. Great. Now let's look at requirement 2. We need faster than 10 milliseconds per inference. So again, it's just a very simple pandas query. If you're familiar with pandas, you will find this very familiar. And the last thing that we're going to do is we are going to filter all of those results for stuff that can't consume more than 200 millijoules per inference. So let's filter our data frame. Great. So we see that there are still several hundreds recipes that meet all three of our requirements. Now let's look at what these recipes are. Just take a quick glance at the resulting data frame, and we can see that most of them are quantized with our symmetric PC quantizer. Most of these are YOLOs. Actually, I see a lot of YOLO V5, but of different sizes, some extra large, some medium. I see some YOLO V8s as well. Interestingly, I also see some efficient bit models. So you can see here that each of these are tabulated with their inference energy and inference max and all the information that you might be interested in. And once you have these recipes filtered out, training them on your data is super simple. You ingest your data with our Recipe Designer API, and you load each of these recipes from their SPPR, basically a serialized representation that's sitting right here on the data frame, and you train them on your data. And once you've trained on your data, you can very quickly evaluate the performance on your data and pick the best performing recipe for your specific data out of the very many that you were able to train. And you have guaranteed that it will meet your performance envelope on the hardware that you're interested in, because things like inference time, memory consumption, and energy consumption, for example, are things that are data independent or data agnostic. They're really about the model graph, which stays basically the same regardless of what data you use for training. Okay, so we were able to see just now with the visualizer for recipes and the actual code that you can filter out our LEIP recipes for the space of recipes that meet your requirements and get to training and deploying those recipes in minutes instead of months. Now, we don't deploy a model to just put it on the hardware and forget about it and never revisit it, right? Like all models, as our projects have a life cycle and need to be maintained, and sometimes changes are necessary. So how does LEIP Design enable you to make changes during the life cycle of your model? That's what scenario 2 is all about. So what if months after deploying to your Orin devices, you get access to Jetson Xaviers? Maybe another group in your organization purchased them and they don't need them anymore. They offer them to you for free. Can you deploy the same model that you already trained? Can you even meet your requirements for inference time and energy in the Xavier? Say if you were willing to retrain. Without LEIP Design, you have to reject the offer of the free Xaviers because there is just too much uncertainty around changing the hardware at this point. Or maybe you get one of the Xaviers first to try and you spend months and months trying to get the model in, maybe to only find out that it doesn't really meet your requirements. Let's look at our scenario 2, the need to change the hardware from the Orin to the Xavier. The first thing we're going to do here is, with the drop-down for target architecture, I'm going to select the Xavier device because I want to see only recipes that have been benchmarked for the Xavier. My biggest question right now is, can I accept these Xaviers? I know there are less expensive, smaller, less older devices under a different NVIDIA architecture. Can I even get those 10 milliseconds per inference for a detection model on the Xavier and keep also my inference energy requirements? So I here now see benchmarked recipes on the Xavier, again on the y-axis relative accuracy and on the x-axis inference time on milliseconds. The 10 is over here. So I still have some recipes that meet my inference time envelope. Of course, there are not as many as we saw on the Orin, but that's okay. We still see some recipes. And this is a smaller hardware device, so we're not too worried about energy consumption. Now let's move down here and filter a recipe, very similar to what we did before. We're going to now do it on the code side. So the first thing we're going to do is filter our entire data frame for only those recipes that can be deployed and have been benchmarked on the Xavier. The same question, can I even meet my power and speed requirements? So we filter the data frame and you see that yes, indeed, there aren't as many as before. This time is over 100 for this particular volume, but there are still some recipes. And let's look at these viable candidate recipes. We see, of course, some of the YOLO V5s, YOLO V8s. So at least on the top 24, they all look like YOLO models. And we see some of them are quantized with symmetric PC quantization. Some are not quantized. Of course, some of the smaller models are not quantized. Okay, very interesting. So now the question arises, can I reuse any of the recipes that I already trained? So with LEIP Design, we're really trying to get super hyper efficient. What if I needed to deploy something on the Xavier today? Today, I don't have time to retrain. I don't have time to see which of these recipes would perform well once I train them on my data, because that's the longest part of the process. So what I've done here is a very simple, give me all of the recipes that met scenario 1, the ones that I already trained for the Orin to find out which was the best candidate recipe for the Orin. And now let's look at all the ones that are candidates for the Xavier. And if there are any recipes that meet both Xavier and Orin requirements, tell me. And we see here there's actually 5 recipes that we already trained because they were part of those 25 best viable candidates for the Orin that we can also redeploy on the Xavier. So you can see incredibly, we have changed this whole picture from not knowing if you can take those Xaviers because you don't know even if you can meet your inference requirements on that device, to saying, yes, I can meet those requirements. And here, I'll give you a model right now that I already trained that I know fits that hardware envelope. And let's deploy with the LEIP SDK and immediately throw it over to that Xavier device and do inference. Today, we talked about how LEIP streamlines workflows and delivers trusted performance, all using a developer-friendly toolkit. We also talked about how LEIP Design builds in ML expertise, letting you start training on your data in minutes instead of months. Whether you're a data scientist, a software developer, or an ML expert, our tools meet you where you are. With LEIP Design, you can find your best model quickly, understand how it will perform on the target hardware of your choice, and know that you're using the best hardware for your needs.